Hey, my name is Christian Ian. I'm UP number 825241, and for my mathematical elements for games and animations artifact, I decided to implement an object transformation sandbox. I chose this type of project because I got inspired by a few of the suggested case study presented by the lecturer, such as probe manipulation and 3D simulation of the solar system. The main objective of the artifact is to match the rotation, scale, and position of the current object with its target in that particular order: rotation, scale, and position. The tasks are being indicated using a text game object from the UI system of Unity. Once the rotation is matched, the colored object turns blue, and the text update is set for the next requirement. In here you can see my rotation method, which checks to see if the button for rotation has been pressed. If so, the user has 3 possible rotations, and these are being performed while keeping pressed the button corresponding for each axis, such as X, Y, and Z, and the direction of the rotation using left or the right arrow. I clamped these values from -1.8 to 3.6 to be easier for the user to match the respective values. This is a part of my transform script, which simulates the pre-built-in transformation script made by Unity, where the user is able to perform matrix transformations such as translating, rotating, and scaling to an object. First, I created my own class which holds information about the matrix. In there I created a method which allows the user to multiply a 4x4 matrix with a vector 4, and by doing this, now the matrix transformation can be applied to the vertices of the object by multiplying the vertices stored in the vector 4 with the information of how we want the object to be transformed stored in the matrix. For performance sake, I kept all 5 of the matrix transformation inside of a matrix called M by creating a new method which multiplies 2 4x4 matrices together, keeping in mind the correct order of doing such transformation, which is translation first, and then the yaw rotation, which is happening on the y-axis, pitch rotations, which is happening on the x-axis, and the roll rotation, which is happening on the z-axis, followed by scaling. And I multiplied that M matrix with the rest of the vertices of the object. In this way, M has to be called once for each model rather than being called once for each vertex in the model, making the whole process much more optimal. In here you can see the function which checks to see if the rotation is being matched, having a 0.5 margin of error. This is the function which scales the object on each axis up and down using the S key for growing, respectively the C key for shrinking. In this function, the scales are being checked, having a 0.35 margin of error. This function updates the position of the character using my own transformation script created earlier on the X and Y axis. The movement is being possible by adding to the initial position of the object a directional vector multiplied by speed and time, followed by a function for the movement on the z-axis, which is analog as in the x and y movement. For collision detection, I chose to use bounding circle collision because of its easy way of being implemented and for its high accuracy. First, I created a class which holds information about the circles, having a center point and a radius. Then the intersection is being checked by comparing the length squared of the distance between the two circles with the radius combined of the circle. The length is being obtained by using my own function. For my camera follower method, I chose to use linear interpolation to obtain a smooth position, having almost no loss in precision when dealing with floating pointing values. The only problem is that I couldn't access the position of the camera using my own transformation script due to an error which was asking for the mesh of the camera, and I had to use Unity's position. The way that linear interpolation works is that if two values, a start and end, are known, then we can find an interpolated value which is calculated using a fractional value, usually between 0 and 1. This is the method which updates the second camera, again using Unity's built-in transformation by multiplying the pitch and the yaw values with 2 different speeds and with the position of the mouse. All of these are being stored in a vector tree, transformed into a Euler angle, and then applied to the object. In this situation, I came across to a strange error after applying my own Euler angles. When I was moving the mouse, the camera started to have a similar motion of vibration rather than having the desired rotating motion, so I had to use Unity's Euler angles instead. In here we have the function which checks to see if all the transformations are being matched, started by rotation, followed by scale and position. When all of the above are matched, the object resets to its position and the start object changes to the next object. When the last object is being matched, A game over game object text will be displayed followed by the exit of the artifact.